everyone, welcome to our channel Electron Chemistry Tutorial. I am Vijayalaxmi. Now let us discuss objective bits on Debrogli wave theory and Heisenberg uncertainty principle from atomic structure. Okay, so in before video we have done some important bits on Bose theory and hydrogen spectra. If you haven't watched that video, please watch that video. That is really help for you. Okay, let's go to the today topic. Okay, first of all, so what is the formula of Debrogli? So Debrogli wavelength of a particle like electron is inversely proportional to its momentum. Wavelength of a particle like electron in motion is inversely proportional to its momentum. H bar lambda is equals to h by p. Okay, so that's momentum nothing but the product of mass and velocity of that particle like electron. So lambda is equals to h by, instead of p we have to write mv. So then lambda wavelength of that particle, a Planck's constant, its value we know very well, 6.626 10 power minus 34 joule second, or 6.626 10 power minus 27 erg second. Okay, so m means mass of a particle or electron, velocity of that particle or electron. So given particle, simply given electron. So this electron revolve around the nucleus, so in a wave like motion around the nucleus. If here two ends of the electron wave meet to each other to give regular crest and troughs, so that wave is nothing but standard wave, so that wave said to be in phase. So in that case, so Debrogli concept can support the Bose theory, that is 2 pi r circumference of that Bose orbit is equals to n lambda. Okay, if the two waves are not meet to each other, so that wave said to be out of phase, that is nothing but non-stationary waves, then not give regular crest and troughs. Okay, so they are, then 2 pi r is not equals to n lambda, means circumference of that Bose orbit may be less than or more than the n lambda, integral multiple of wavelength. Clear? So the next Heisenberg uncertainty principle. So according to Heisenberg, impossible to determine the exact position and momentum of that electron in an atom simultaneously. Okay, so Heisenberg gives the relation delta x, so the uncertainty in position, uncertainty in momentum greater than or equals to h by 4 pi. Okay, so that is nothing but here momentum nothing but, so what, product of mass and velocity, so this is written as m into delta v. So instead of delta p we have to write delta v, this m will goes to here. So simply what is the formula? Delta x into delta v greater than or equals to h by 4 pi m. Okay, suppose if you know exact position, that is delta x 0, so delta v is means uncertainty in velocity will be infinity. If you know delta v is exactly, so uncertainty in position will be infinity. Okay, we can't find out both exactly simultaneously. We can find out only maybe position of that electron or velocity of electron. Clear? So this is what Heisenberg uncertainty principle. So we will do some bits on these formulas. Okay, let's start. First problem on Debrogli. The Debrogli's wavelength of a particle with 1 into 10 power minus 3 kgs and velocity 100 meters per second. So what he has given, we have to calculate wavelength, but mass of a particle given as 1 into 10 power minus 3 kgs. Then velocity is given as 100 meters per second. So what is the relation between them? Lambda is equals to h by mv. H we know very well in meter, joules per second, 6.626 10 power minus 34 joule second by 1 into 10 power minus 3 kgs only, and 100 meters per second, nothing but 10 square. By simplifying this, 6.626 into 10 power minus 34 into here 10 power minus 1, remaining 10 power minus 1 will become plus 1. So how much? 6.626 10 power minus 33 only meters. So this is what lambda. Clear? Second problem. So this is previous bit. If the de Broglie wavelength of the electron in nth orbit, nth Bose orbit in hydrogen atom is equals to, wavelength is equals to simply 1.5 pi a naught. Here a naught is Bose radius. So then the value of n by z. So then a de Broglie wavelength is given. Lambda is given as 1.5 pi a naught. Okay. So then circumference of that Bose orbit 2 pi r is equals to n lambda. Okay. So then 2 pi r is given as radius. What is the formula of radius of nth orbit? 0.53 into 10 n square. So for hydrogen like atoms z. To calculate the n by z, so we have to take this hydrogen like formula for hydrogen like species. Okay. So instead of 0.53, he gave a naught. So simply write down instead of r n a naught into n square by z. So this is written here instead of r. A naught into n square by z, that is equals to n lambda. So n square here n mutually cancelled. Okay. So then 2 pi a naught into n by z, that is equals to lambda. We have to calculate n by z only. N by z nothing but lambda by 2 pi a naught. So this lambda is given as how much? 1.5 pi a naught. 2 into pi a naught. This pi a naught mutually cancelled. Okay. So then n by z is equals to 1.5 by 2. So multiplied with suitable integer to get whole numbers 3 by 4. So what is the ratio of n by z? 3 by 4 only. Clear? Next third problem. The de Broglie wavelength associated with a photoelectron varies with frequency of that incident radiation as. Okay. U naught is given as threshold frequency. Okay. So de Broglie, we have to related both the de Broglie wavelength of lambda and frequency of photoelectrons. Clear? For that we have to write both formulas. Lambda is equals to h by mv. For this is what de Broglie wave theory. De Broglie's equation or wave equation. So for photoelectric effect. So what is that incident radiation? H nu is equals to h nu naught plus Ke. Okay. Then Ke is equals to how much? H nu naught. That's simply h into nu minus nu naught. Okay. We need to give the relation between the lambda and frequencies. Okay. So for that, h Planck's constant, m mass of electron always constant. Okay. So this is here photoelectron. No, electron is given. So that's why mass of electron always constant, that is 9 into 10 power minus 31 kgs. Okay. So that's why that formula. So h and m taken as constants. So simply ignore them. Okay. So lambda is proportional to 1 by v. Clear? Now here, but kinetic energy is equals to, we know very well, half mv square. So 1 by 2 value also always constant, that is 0.5. So mass of electron here also same constant. So simply how to relate it? V is equals to square root of Ke. Okay, so this is V value. V is equals to square root of Ke right here. Lambda proportional to 1 by square root of Ke. Okay. Now, Ke is equals to what? So, instead of Ke, we have to write this one. So, lambda is proportional to 1 by square root of h by nu minus nu naught. Okay. So, same Planck constant, ignore simply. So, lambda is proportional to 1 by square root of nu minus nu naught. So, this is also written as lambda is proportional to 1 by nu minus nu naught whole power 1 by 2 instead of square root. So, we can write 1 by 2 only. So, this is the answer. Clear? Next, fourth problem. The uncertainty in momentum of an electron is 10 power minus 5 kg meters per second. The uncertainty in the position. So, what is the Heisenberg uncertainty principle? Delta x into delta p greater than or equals to h by 4 pi. So, delta uncertainty in momentum delta p is given as 10 power minus 5. So, delta x is equals to h by 4 pi delta p. So, uncertainty in position can be calculated for h value 6.626 10 power minus 34 joule second. 4 into 5 value, how much? 3.14. So, delta p is given as 10 power minus 5. By simplifying this, we will get 5.27 into 10 power minus 30. Next problem. This is previous bit episode 2016. In which of the following product of uncertainty in velocity and uncertainty in position of a microparticle of mass m is not less than? Very simple here. Delta x into delta v, uncertainty in position, uncertainty in velocity. The product of uncertainty in position, uncertainty in velocity is always greater than or equal to h by 4 pi em. Okay. So, not less than nothing but this is the formula simply. Greater than or equals to h by 4 pi. Simply option is given as delta x into delta v greater than or equals to h by 4 pi into 1 by m. So, this is the answer. So, always greater than or equal to h by 4 pi into 1 by m only, not less than. Clear? See here? Everybody look at me. So, this question asked by one of my favorite student. So, that's why I want to share with you too. Okay? So, listen to me carefully. The ground state energy of hydrogen atom minus 13.6 electron volts. So, the energy of second excited state of helium plus is in electron volt. Okay? So, what is the formula of energy of nth orbit in electron volts? Minus 13.6 electron volts by n square. So, this is what hydrogen like atom, that's why we need to take Z square. Okay. So, now electrons here, the ground state energy level of hydrogen atom minus 13.6 electron volts. No? Second excited state of this helium plus electron. Simply here, helium plus nothing but it has only one electron in 1s orbital. Okay. So, first orbit, second orbit, third orbit. Okay. So, simply this 1s electron present in here, so it excited from first level to second level in first excited state. excited state, and second level to third level in second excited state. Second excited state. So in second excited state means I have to take which orbit here? N is equals to 3 here. Clear? So simply minus 13.6 by 3 square into what is the atomic number of helium? Z is nothing but 2. So 2 square. Okay. Minus 13.6 by 9 into 4. One's how many times? 1.51. Okay. By multiplying these two, we'll get minus 6.04 electron volts. This is also previous date. It came in 2019 JEE mains. Okay. Next, wave mechanical model. So this was developed by Erwin Schrödinger and Heisenberg. So according to this Schrödinger wave equation, dou square psi by dou x square plus dou square psi by dou x y square plus dou square psi by dou z square plus 8 pi square m by h square into E minus V into psi is equals to 0. Here psi is equals to wave function. So electron wave function in 3-dimensional space. Okay. According to this wave model, so path of the electron never be find out exactly around the nucleus, but we can find out a region of electron space around the nucleus where probability of finding electrons. We can find out region of electrons but not the path of the electron, exact path of the electron. Okay. So see that psi is nothing but simply here suppose 1s orbital is there. So 1s orbital, 1s electrons can find out around the nucleus. The sphere where probability of finding electrons, the 3-dimensional space around the nucleus where probability of finding electrons maximum to the extent 90 to 95% is called simply probability function or D function, simply orbital. Okay. So that probability function is nothing but 4 pi square r into dr psi square. Okay. So dr nothing but distance between this probability function. Okay. So this is 1s orbital, then 2s orbital, 2s orbital, then 3s orbital. Okay. So here this empty space where the probability of finding electrons is 0. So the 3D space around the nucleus where probability of finding electrons is very less, that is 0, is nothing but they are called simply node or radial nodes. Radial nodes can be calculated by formula n minus L minus 1. N means the principal quantum number, L means orbital quantum number minus 1. N minus L minus 1 is very important formula. Okay. So next. So here suppose you want to draw the curves. So this is for 1s orbital, 2s orbital, 3s orbital. Okay. Simply this peak of the curve, the psi value above the axis positive, below the axis negative, along the axis 0. So simply this peak of the curves can represent the probability of finding electrons. Okay. Probability of finding electrons at that region, at the space. Clear? Next. So orbital, shape of the orbital, we have S, P, D, F orbitals. Okay. So S orbital has spherical shape, have no directional character. So spherical means there is no x direction, y direction. So in all directions we can find out probability of finding electrons around the nucleus. That's why S orbitals are spherical in shape. Okay. So the size of the S orbital increases with increase in the n number, means what? Principal quantum number. Okay. So the here principal quantum number 1, 2, 3. As n value increases, size also increases. Okay. Clear? So here this is 1s orbital, 2s orbital. Here size, here also size, here some more distance. Okay. Next. Here, so for S orbital, orbital quantum number 0. So remember this. Orbital quantum number is 0 for S orbitals. Next, P orbitals have dumbbell shape. So these are 3 degenerate orbitals. Px, Py, Pz all are have same energy in same orbit. Okay, so maybe that is 2px, p orbitals starts from second energy level, 2px, 2py, 2pz, or 3px, 3py, 3pz. Okay, so px means two lobes present on the x-axis, that px orbital, present on the y-axis, that py orbital, present on the z-axis, that is pz orbital. Okay, next d orbital. So here orbital they have directional character in x, y, z direction. Orbital quantum number 1. Here orbital quantum number 0, here orbital quantum number 1. Okay. Next d orbitals. So d orbitals have double dumbbell shape. So these are 5 degenerate orbitals. They are dxy, dyz, dxz, dx square, y square, dz square. dz square. So now dxy, dyz, dxz are lobes. The 4 lobes present in between the x and y axes. Here, so lobes in between the y and z axes. Lobes in between the x and z axes. So, but here dx square, y square, 4 lobes present on their axes. Okay. So, but dz square orbital have 2 lobes only, and there is a ring of electron cloud around the nucleus. Around the center, okay. So simply each d orbital means d orbital have orbital quantum number 2. Clear? Next, f orbital. So these are 5 degenerate orbitals, dxy, yz, x square, y square, z square. Okay. Then next, say f orbitals. These are 4-fold dumbbell shape. So these are double dumbbell, no? So double. So next time. So double dumbbell means double dumbbell shape. Means 4-fold dumbbell is very complex structure. Okay. So they have 7 degenerate orbitals. They are f x, x square, y square, f y, x square, y square, f z, x square, y square, f x, y, z. And f z cube, f y, z square, and finally f x, z square. So these are 7 degenerate orbitals. Their starts from fourth energy level. Okay, their orbital quantum number is 3. Okay, so they starts from first energy level. S orbital starts from first energy level, n is equals to 1. P orbital starts from second energy level, n is equals to 2. So d orbital starts from third energy level, n is equals to 3. F orbital starts from fourth energy level, n is equals to 4. Okay, but here L is equals to 0, here L is equals to 1, here L is equals to orbital quantum number 0, 1, 2, here 3. Okay. So I want to tell you one more point here, nodal plane. So nodes are radial nodes, nothing but the space where probability of finding electrons 0. So but the plane where probability of finding electrons 0, the plane is nothing but nodal plane. So nodal plane is equals to azimuthal quantum numbers. So for s orbital there is no nodal plane, azimuthal quantum number 0, there is no nodal plane. So p orbital azimuthal quantum number 1, there is each p orbital has one nodal plane. Suppose for example, for px orbital, nodal plane in between the y and z axes. So this is what? This is nodal plane. So in between the y and z axes, there is no probability of finding electrons here. Okay. So py orbitals in between the x and z axes. Backside, you have to imagine backside. Okay, so here there is no probability of finding electrons in between the x and what? Z. So for Vz orbitals there is a nodal plane in between the x and y axes. In between the x and y axis plane there is no probability of finding electrons in that plane. So that's why 0, electron probability 0, that is nodal plane. Nodal plane is equals to azimuthal quantum number. So if azimuthal quantum number 0, there is no nodal planes. Maybe 1, nodal plane 1, 2, nodal planes 2, 3, nodal planes 3. Okay, so see here, the orbitals, each d orbital has two nodal planes because of orbital quantum number 2. Orbital quantum number 2. So here L is equals to 3. So each f orbital has 3 nodal planes. 3 nodal planes because of orbital quantum numbers 3. Clear? So remember this. So it's very important. Nodal planes, radial nodes. So it's very important. The shape of the orbitals also important. First problem, wave mechanical model. The electrons are more likely to be found. See here by this graph. So the probability of wave function more at A point and A region and C region. Okay. The electrons are more likely to be found at A and C regions. Simply you have to select this option. Okay, this peak of the curves can represent the probability of finding electrons simply. Okay, maybe are they above the axis or below the axis. You can select simply at A point and A region and at C region. So we can more likely to be found electrons. But at B region there is no probability of finding electron. This is node. Clear? Next. The graph between the probability function or probability density I square and radial distance r. So shown in below. So this represent the which orbital? Okay. So simply here. So this means simply here. This is for 1s. This is for 2s. This is node. Simply it represent the simply 2s orbital. 2s orbital only. So these two are previous bits 2019 JEE Mains papers. Okay, very simple bits. Okay, next. Third problem. The number of radial nodes for 3s 3p orbitals. So what is the formula for radial nodes? Radial nodes is equals to n minus L minus 1. Okay. So for 3s orbital radial nodes, 3 means n is equal for 3s orbital, n is equals to 3 but L is equals to 0. So simply n minus L minus 1 nothing but 3 minus 0 minus 1. How much? 2. For 3p orbitals, n is equals to 3 but L is equals to 1. So then n minus L minus 1 for 3p orbital nodal radial nodes, 3 minus 1 again. Okay. Simply you have to select radial nodes for 3s orbital 2, 3p orbital 1. Okay. Next. So this is also previous bit MSET 2015, this is MSET 2013. The number of radial nodes, same question, present in the 3p orbital, same here. Okay, 3p orbital. 3p orbital, what is the 3p? Nothing but n is equals to 3, L equals to 1. So n minus L minus 1, that is equals 3 minus 1 minus 1, that is equals to what? 1. Suppose instead of 3p, maybe 2p is there. So how to find out? N minus L minus 1 means n means how much? 2 minus p per p orbital, any p orbital, 2p, 3p, 4p, 5p, 100p also orbital quantum number 1. Okay, 1 minus 1, how much? 0. Clear? So listen to me carefully. So for 2p orbitals, radial nodes 0, for 3p orbital, radial nodes 1. Next. So this is also previous bit but NEET 2016. Okay. Which of the following pairs of d orbitals will have electron density along their axes? Along the axes. Okay. So these all are d orbitals, but only d x square y square orbitals, d z square orbitals, 4 lows present along their axes, no. So simply this is x y, 4 lows present on their axis, x axis, y axis. Here 2 lows present on the z axis and there is a ring of electron cloud. Okay. For dx square y square and dz square only, electron density present along their axes or loss present along their axes. Simply you have to select which option? Third option. Clear? See your next problem. The number of nodal planes for px orbital. Nodal planes nothing but nodal planes is equals to azimuthal quantum number. Azimuthal quantum number. Px nothing but for any p orbital. Any p orbital nothing but maybe that px orbital or py orbital or pz orbital, or simply that is maybe 2px, 2py, 2pz orbitals, or 3px, 3py, 3pz orbitals, 4p, maybe 100 px, py, pz orbital. Any p orbital nodal planes are same, that is 1 only, because of azimuthal quantum number is 1. Clear? So simply for px orbital azimuthal quantum number 1 in what? X in yz plane. Okay. So this is what px orbital. In between the y and z, so there is a nodal plane. So this is what? Nodal plane. Clear? Next. The density of electron cloud of orbital dxy in yz plane. So I have to draw dxy, xy. So 4 lobes in between the x axis and y axis. But in between the y and z means you have to imagine back side. In between these two there is no probability of finding electrons. Means in yz plane there is no probability of finding electrons. So that's why electron cloud in yz plane is 0. So that is what? Nodal plane. Nodal plane. Clear? Next. The number of angular and radial nodes. Angular nodes nothing but nodal planes. Okay. Radial nodes for 4d orbitals. So simply angular nodes nothing but nodal planes. Nodal planes. That is equals to azimuthal quantum number simply. Azimuthal quantum number. For d orbitals, for any d orbital, for any d orbital, L value is 2. So for 4d orbital, angular nodes means nodal planes is equals to 2. Next, radial nodes. What is the formula of radial nodes? N minus L minus 1. Okay. So here for 4d orbital N value 4 but L value 2. So then find out. That is equals to N4 minus 2 minus 1. How much? 1. So angular nodes 2 and radial nodes 1. This is also previous by 2014 MSET. Okay. Next. A certain, this is previous by 2021 JEE Mains. A certain orbital has n is equals to 4. M magnetic quantum number is equals to minus 3. The number of radial nodes in this orbital. Simply here n is equals to 4, m is equals to minus 3 nothing but L value should be 3 only. So then only m values are minus or plus 3, minus or plus 2, minus or plus 1, 0. Clear? So we will discuss in next class clearly about quantum numbers. So just remember this, maybe m value 3 nothing but that L value should be 3 only. Okay. So now radial nodes formula n minus L minus 1. Okay. So simply 4 minus 3 minus 1. How many radial nodes? Radial nodes? 0. That's all for this video. You have to do some more bits on this topic. If you have any queries, please write a message on the chat box. Okay. In the next video, we will do quantum numbers and electronic configuration. That is very important. Don't miss that video. Okay. So did you like this video? Please like, share, subscribe my channel to get more videos. Thank you for watching this video. Thanks a lot.